If you're an engineer, you know this feeling. You're deep into debugging a system, and the failure, it just disappears. Poof. You can stress test it for days, and the root cause is just nowhere to be found. It feels like you're chasing ghosts, right? The frustration is so real. But what if the problem isn't you? What if it's the very nature of the systems we've all built?
This quote right here, it just gets to the absolute heart of the issue. This isn't about engineers suddenly losing their touch. It's about a massive, fundamental shift. The complexity of our tech, from the silicon all the way up to the cloud, it's just accelerated to a point where our human ability to debug, to find that one needle in a universe of haystacks, just can't keep up anymore. We're staring down a whole new class of problem that our old methods were never, ever designed to handle.
And this visualizes our new reality perfectly. You've got human debugging speed, right? It gets better, but it's a pretty straight, linear improvement. But then you've got system complexity and all the interactions between components, and that's just exploding exponentially. See that widening gap between the two curves? That's what we call the risk delta. It's this danger zone where these unpredictable, catastrophic failures are born. And that gap, it's become unsustainably wide.
Okay, so if our old methods of hunting for a single root cause just aren't cutting it anymore, what are we actually fighting? What is the real enemy that's lurking in that risk delta? Well, the answer is something that operates invisibly. It accumulates over time until it's just way too late. It's called silent drift.
Think of it like this: a huge outage, the kind of thing that makes the news. That's just the tip of the iceberg. It's the visible, dramatic event that everyone sees. But the real danger, the true mass of the problem, is this enormous, invisible, silent drift happening just beneath the surface. Most of these catastrophic failures don't just happen out of the blue. They're the final, explosive outcome of this slow, hidden decay.
So what is silent drift, really? It's not one single thing, and that's what makes it so tough. It's the slow, invisible degradation of system health across literally countless layers. We're talking about margin decay in your silicon, thermal instability in power modules, firmware versions slowly diverging across your fleet, all these tiny, almost imperceptible shifts just piling up over time, creating the pressure that leads to a sudden system-wide collapse. And listen, this isn't some abstract theory. These are real-world problems. It's that slow creep of SSD tail latency that eventually causes major business timeouts. It's the degradation of thermal paste that leads to grid failures. It's signal and power integrity getting distorted over time. Jitter accumulating across a network. Different firmware versions causing these subtle, weird inconsistencies. Even something like the meaning of an API slowly drifting from what it was originally supposed to do. None of these things are screaming failure on their own, but together they're whispering that the system's intent and what it's actually doing are drifting further and further apart. So, to fight an enemy like silent drift, you can't just have a better tool. It's not enough. You need a whole new philosophy for how you even think about and build reliable systems. A philosophy that's designed from the ground up to see the unseen and to govern that drift before it becomes a disaster. This new approach, it's really built on 3 fundamental laws. First, build the core before the shell. That means no empty abstractions. Every single component has to be a complete operational core from day one. Second, see reliability as a vector economy. All that drift, that's data. We need to convert these invisible drifts into measurable, actionable vectors. And third, incentives drive stability. A system only becomes truly reliable when there's real accountability, aligning the goals of everyone: operators, manufacturers, and cloud providers. Now, a really key part of this whole philosophy is moving beyond the simple signals we're used to seeing on our dashboards. A traditional signal is a scalar. It's just a single value, like CPU is at 80%. It just vibrates in place. But the new way thinks in what we call causal vectors. A vector has magnitude, direction, and momentum. It doesn't just vibrate, it actually propagates through the system. It tells you not just what's happening, but where it's going and why. And that is absolutely essential for predicting causality, not just reacting to effects after they happen. Okay, so we've got this new philosophy. It's all based on vectors. Sounds good, but how do you actually implement that? The answer isn't to build yet another monitoring tool that sits outside the system looking in. The answer is to build an architecture that lives inside of it.
And this is the XR architecture. The crucial thing to understand here is that it's not some external observer. It's a unified fabric, almost like an embedded organism. Its components, all interconnected by this causal fabric called XR bus, live across every single layer, from the physical domain, capturing silicon-level truth, to the governance domain that enforces boundaries, all the way up to the cloud and even an economic domain that actually puts a value on reliability. It connects the silicon, the firmware, the OS, and the cloud into one single causal mesh.
Let's do a quick roll call of the key players that make up this fabric. First, down in the physical truth domain, you have XSM and XRAD. Their job is to capture raw physical signals to reconstruct the causal story. Then, up in the governance domain, XXenos acts as a boundary governor, while XAPS translates issues into solvable problems. At the cloud and scale level, XROG provides governance across entire fleets and even multiple clouds. And finally, the economic components, XRAS and XRC, they're designed to actually quantify reliability itself, creating real, tangible incentives for stability.
So how does this all actually work in practice? Let's take that silent drift example of the SSD tail latency. Step 1. Detect. XSM and XRAD see a tiny, continuous increase in latency. They identify this trend as a drift vector, even though no alert threshold has been breached. Step 2. Analyze. The system projects this vector forward and calculates that, on its current path, it will violate the business SLA in about 30 days. Step 3. Recommend. XApps generates a clear, proactive ticket. And Step 4. Prevent. Maintenance is performed before any customer ever feels the impact. And just like that, you've turned a potential major outage into a routine, non-destructive fix.
This ability to prevent a failure before it even exists isn't just about one SSD or one server. When you really zoom out, you see that the ambition here is much, much bigger. It's about weaving a new, reliable foundation for everything we build on top of it. It's about architecting the reliability fabric of civilization itself.
This slide, this captures the full vision. A single, unified reliability architecture that spans everything. I mean, everything. It starts at the lowest possible level, the silicon itself, and it extends all the way up through firmware, the operating system, entire compute nodes, edge devices, and finally across these vast, multi-cloud topologies. The goal is absolute, to create a system that can detect failures before they can even exist, governing the silent drift that causes those catastrophic cascades we all fear.
So the fundamental takeaway here is this. We often think of reliability as just a feature, or a metric to track after the fact. But this new philosophy reframes it completely. Reliability isn't just another layer you add on top. It is the fundamental, hidden architecture that everything else depends on. And by architecting for it from the ground up, we can finally begin to build systems that are truly worthy of our trust.